Hey everybody, welcome back to Organic Chemistry. In this video, I'm going to go over the problem solving that I assigned for the NMR spectrums. So this is the wrap-up video. This is the last video for this chapter. And what we're going to do is, actually the way I'm going to approach this is, I didn't solve the problems yet. I didn't even look at them because I want to try to approach it for the first time with you guys. And so this way you're going to get, my approach. So this could either backfire, or it might work great, or it might not. In the past, I've done things like this and it works fine. But I think that for NMR, it's best for me not to have solved it before I do it on video, so that this way, together, we can actually approach the problem and kind of analyze the way things are working. Okay, so this is the last video set for this chapter. And then after this, I'm going to do the workshops that are related to NMR. Okay, so let's get started. Now, these are the problems that we're going to do. Handout number 23 through 25, and then Solomon 10th edition, question number 39, D through K. And again, if you have an older edition, it's definitely in the same chapter. It's at the end, and you'll see a whole bunch of questions, as we'll see in a moment. Now, before we begin, I just want to mention that this is the chart that I'm going to refer to, and you should probably print this out. I'll keep it clean so that you have a clean print. Actually, I'm sorry, I put up a clean copy on the website so you can see it. But yeah, so you should print this out because I'm not going to refer back to this. I'm probably just going to talk about it, and I'm assuming that you have this chart in front of you. This chart is not as necessary. I just figured in case there's a problem that requires this, this type of analysis, I'll come back here if I need it. And finally, this is the IR chart. And again, this is something that you should have from your textbook. And I'm not sure how much we're going to need it. But like I said, I haven't seen these problems. I didn't look at them. And so, it's beyond me whether I know if we're going to need it or not. The only thing that you should know is at least this up here. This is a good, useful little summary. And I gave this to you back in the exam when we learned about this material. This kind of gives you a general overview. Okay? So at a minimum, you should have this little diagram in front of you, and I don't think we'll need all this information down here. Okay, let's get started. So the first problem, it says identify isomers C and D, and the molecular formula is C4H8O2. So let's do a quick IHD. Actually, let me just analyze the rest. So here it's 1700. Remember, anywhere from 16 to 1800 is a C double bond O, right? So if we go back right here, anywhere from 16 to 1800, C double bond O. It could be a C double bond N or C double bond C, but the fact that I see an oxygen, it's probably going to be the C double bond O, right? But the one thing I do note here is that I see two oxygens, and I only see an IR of 1700. So there's nothing in the 3000 range, right? Which would be the OH. So this is not a carboxylic acid. That is my guess, because if it was, we would have an IR to support an OH at the 3000 range, right? So this must be like an ester or an ether and a carbonyl, one of those two. Probably an ester, if I had to guess, but we don't know yet, so let's take a look. C4H8O2. So let's do a quick IHD. C4H8. Now, if we had an alkane, it would be C4H10. We're subtracting those out. Remember, for the oxygen with IHD, we just ignore O, right? That's what we were told when we did IHD review. You just ignore the oxygen. It has nothing to do with the H count. So minus is subtracting out is -2 is 2. Divided by 2 equals 1. So we have one IHD. That means it could be a double bond or a ring, and we already know it's a double bond, right? It's a double bond O. So that's what the 1700 tells us. So at this point, I know I have a carbonyl, but I also know that there's no rings and there's no alkene in the system, right? So there's no ring and there's no alkene, because we already know we have a C double bond O, and that's what gives us that one IHD. All right. So now look over here. So I guess what we could do next is maybe integration. And as you see here 23, 29. Well, you just have to divide everything by 10 in this case, right? So you get it to 3, 2.9, 2.3. So actually, what this is remember, this is our ratio stuff that we talked about, the integration numbers. And so you have to kind of, whatever you divide one by, divide the rest by. And so I'm going to bring this down by I'm going to divide it by 10 in order to get this to a 2.3, because that's closer to the number of H's. Remember the rule. When you have a number of H's given, then these right here have to add up to that number, right? So obviously 23 is big, and that's why I'm going to divide it by 10. So if I just divide this by 10, divide that by 10, and that one by 10, now we have 2.3, 2.9, and 3.0. And even further, we could round, right? So we could just round this up, or this one down. I'll round this up. So I'm guessing that this is really, and this is just like a rough approximation, but if it adds up, then we're right. I'm guessing that this is a 3 instead of 2.9, right? So divide by 10, you get 2.3. But then I'm going to just say, all right, forget the 3, just 2. And now let's see if we're right. So this right here, we could just say is 3. And so we have 3, 6, 8, and that's how many H's we're supposed to have. So I know now that I've figured out my H count for each chemical shift. Now, let me point out a few important details as I'm looking at this. The first one is that this right here is a blow up of this chemical shift. So our chemical shift is here, here, and here. Whatever else is above, if it's above the chart, that means it's a blow up of that right there. Okay? So this one, they don't give us a blow up because it's a singlet. But this is a quartet and this is a triplet. All right, so hopefully all this is making sense. And again, if you see a big number like 20 or 30, just divide it by 10 and you're probably right. And that's, basically how that would work. Okay. Okay, so that's what I would suggest, okay? Just divide it by 10. And again, you could always round, right? This is close to 3 and this is close to 2. So if it was 2.5, then it's on the fence. And then I'd work this out and figure out how many H's. If there's an extra H, I'd add it here, and if it wasn't, I'd subtract it. So I think that's kind of clear. All right. Now, what else can we get from this? Well, we know now that this right here is a CH3, right? This is a CH3, and this is a CH2. And I think that's about all we really need. And for this problem, I'm analyzing, and here's what I'm saying to myself. Let me tell you what I'm thinking. I've done pretty much the basics. I've got my IHD. I realize there's no fancy stuff going on. Double bond ring. It's right here. It's clear, right? And I know I have 4 carbons. I already figured out from this that I have these groups here by just, working with the integration numbers, right? I'm not even looking at the splitting yet. I don't care about that because I have so much information already to get started. I have a carbon, 4 carbons, and 3 of them are taken care of here. And actually, I know the 4th is that. And I also know it's not an aldehyde, right? So maybe that's something. So let's do a quick, is it aldehyde? And the answer is no. I'm saying this in my mind because there's nothing over here. It's not even going at 10 to 12. It stops at 8. So there's no aldehyde, right? The answer is no. So, it makes sense that this carbon is in the middle, so it doesn't have any H's. So we already have our 4 carbons right here. We have 4 carbons in our formula, and I see the 4 carbons, methyl, methyl, methylene, and carbonyl, ketone, right? Or ester. Okay, so let's go ahead and start putting this together. So I'm going to start, as always, I always start with the functional group that's of importance, and that would be my carbonyl. And I know that this has a carbon on both ends. Now, actually, it doesn't have to be a carbon. It could be an oxygen. But right now, I'm just going to assume for sure that it's connected to something on both ends. It can't be an aldehyde, right? It might not be a carbon. It might be an oxygen. We don't know yet. But let's take a look and figure out what we can do from this. Well, I have a CH2, and I have 2 CH3s. And I also have an oxygen, right? That's my pieces. I have 2 oxygens. I already have one handle right here. Now, notice how you have a split over here. This is a quartet. This is a triplet. And this right here is a singlet, right? So this tells me that there's one methyl that's completely by itself. You see that? Because if it wasn't, meaning it doesn't have any neighbor H's. So this right here is an interesting peak for me because that would tell me that I have a methyl by itself, and it could be like this. It might be with the oxygens here, but I don't think so, and I'll tell you why. Because you see how the singlet's not furthest downfield? Well, this right here represents something that's closest to the oxygen, right? Remember, I showed you guys how if you look downfield, that's going to be closest to oxygen, right? So the fact that I have a singlet right here in the middle of the chart, not at the end, tells me that this oxygen is not near it. Because if it was, it would be furthest downfield, right? So if there was an oxygen over here, then this reading would be the furthest to the left. And that's not the case. So now I know for sure that this is right, because this methyl's by itself. I don't want to put a carbon here or it's split. And now let's think about what we have left. Well, we've got this done, but we still have these two, and they're coupled. You can see that, right? This is a quartet and this is a triplet. So they're splitting each other. And you say, well, how do I know that? Well, n minus 1 here is 3, right? 1, 2, 3, 4 minus 1 is 3. And notice how that's a CH3? And here it's n minus 1 would be 2, right? You minus out one of these lines, you get 2. So that means the neighbor is a CH2, and that's right there. So I know these two are neighbors, and I also know that they're splitting each other, and now I'm ready to solve the problem. Because if I had an O here, and then a CH3, these two would not split each other, right? This right here are now separated so they don't split. And in my chart, it's telling me that they split each other. So let's go ahead and erase that. That doesn't make sense. But what if we put the O here and then a CH2, CH3? Well, that's definitely the right answer, because these two will split. And now let's think about this. Let's label it out. This is definitely A, right? It's the furthest downfield because it's further away from the oxygen here. So this one here is on a carbonyl, which isn't good. This one is on an oxygen, even worse, right? Remember our chart? If we go back to our chart, it tells us that being next to a carbonyl is not as bad as being on an atom with oxygen, right? So this is, replace Z with an O, this H is worse off than being next to a carbonyl. So that's how I know, okay, so this one's better than this one, but this is still worse than that. And so now I know, okay, this must be B and this must be C. C is split into a quartet, 3 plus 1. So this is a quartet. A is split into a triplet, 2 plus 1, triplet. And this is by itself, singlet. All right, now I know everything I need to know, and I always do this, and you better do this on your exam. After you think you have the answer, you better double check that the patterns match up. So A, furthest to the right, is a triplet, then in the middle is a singlet, and then a quartet. And that's what we see here. Triplet, singlet, quartet. So we know this is the correct answer. Now again, let me emphasize, because I know someone's asking this right now to themselves, how did I know that the methyl wasn't next to the oxygen? And it was like this, because this would also give us the same reading on the chart. You would have a singlet, a triplet, quartet, and a triplet. So this would give you the same signature. Do you see the difference? Because right now this is furthest downfield. It's touching O. This would be furthest downfield. There should be a singlet furthest downfield, right? If it was like that, this would be furthest downfield. And it's not. Not in this diagram. There's no singlet over here on the left. So that's why I knew this was wrong, right? So this is not the correct answer. This is perfect. All right, there you go. So we did a nice, thorough analysis, and let's do the same thing again. All right, now this is the other chart. This is interesting, so I'm looking at it. It's the same formula. Identify chart C and D. Oh, I'm sorry. Right, so I copied the question here so that I can see it on its own page. All right, so C4H8O2, same formula, same stuff, right? So we have C4H8O2. We know IHD is going to be equal to 1. And I also see up here a C double bond O. So we have our IHD handled. I don't see anything from the 9 to 10 region, so I know there's no aldehyde, right? Because if there's an aldehyde, we'd have a reading 9 to 10. So there's no aldehyde. All right, and is there anything else from this that I can get? Well, not yet, but now I could see what they're doing, right? It's very interesting because now everything is singlet. So we're going to leverage the second O to make sure that nobody is neighbored with anybody else. No H's have neighbors. So now I know the answer. And this is a continuation from the previous problem. So how I would begin in this case, if I didn't know the last answer, the way I would begin is I'd say, okay, I have a carbonyl. And I know that no one wants to be neighbors. So if I have a carbon here and a carbon here. Well, this one's perfect as it is because it's furthest away from this one here or any H. So this is perfect. But now for this one, I could either put the O here and then CH2, CH3. That would give me splitting. Or I could put a CH2, then an O, then a CH3. Notice what that did? Everybody is separated from each other. There's no splitting. They're all singlets. All right, now this definitely is the answer. And now I want to prove which signals for which. And notice I didn't even do, in this case, I didn't do integration because there was a continuation from the previous problem. So we kind of had a head start. If this was the first problem I did, I would have done integration. Let me do a few now. So this is 1.8, right? And this is 3.0 and 3.1. So I'm going to bring this to 3.0. I'm going to bring that, of course, to the same. And I'm going to raise this up to 2, right? I'm rounding this one up, rounding that one down. So that gives us 8. Right? See that? And that's what we're looking for, 8 H's. So I know this is correct. CH3, CH3, CH2. All right, so hopefully that's clear now. Now, like I said, let's label this out. So if I was to label out of these 3, which is the one to the right? And I hope you're saying this one here. Why? Because this one is furthest away from the oxygen, right? These 2 are touching oxygen. So because they're equal distance to oxygen, it's actually not about methyl versus methylene because this is also touching carbonyl. So this is better than that one, but not because it's methyl over methylene. Although that's true, it is methyl over methylene, but that's not why it's better. It's better because it's only touching oxygen, and this one is touching 2 different groups that are electronegative to it, right? So this is definitely B, this is definitely C, and this would be A, B, and C. Okay? So hopefully that's clear. This is pretty straightforward. I like this problem. It was nice. Good problem. Okay, so now I have C9H10O2. Whenever, like I said, I didn't answer these problems before doing the video with you. So I'm going to tell you what I'm thinking. I'm going to try to do as much as possible. When I see a big formula, right away my eyes draw to here. Because if I see 6 to 8, I know this is a benzene. And sure enough, it is. So that was the first thing I thought of when I saw this formula. And so I want to let you know that. So right away I look, when I see a big formula, I'm looking for signature. 6 to 8.5 is always benzene. And thank goodness it is because that's 6 of my 9 carbons. Right? Okay. And then the other thing I'm going to do, even before I read this, is I'm going to say, okay, if this is 5 H's, remember what that means. It's 1 branch. Right? So now I know I have a benzene with just 1 thing touching it. There's no, remember how that works? Benzene has 6 H's. Every time it has a branch, you have to remove an H and put in a branch. So that means that 1 branch is 4 H's, right? 5 H's. 2 branches would be 4 H's. 3 branches would be 3 H's, and so on. So every time you remove an H, then you could put a branch in. All right. So now I'm looking here, and that's 1700, so I know that's C double bond O. And I still notice to myself, okay, I have 2 oxygens here, so I'm going to keep that in mind. It must be like an ester. There's no alcohol supporting it in this information here, so I'm assuming there's no alcohol. If there was, we would see a 3000 reading, right? But we don't. So the assumption is there's no alcohol. All right, now let's do, I guess, integration. We might as well knock out the rest. This is a CH2, and this is a CH3, right? And so let's count up the number of H's with the number given. And so we have 3, 5, and 5 equals 10. So this is perfect. I know that this is not a ratio. It is the exact number of H's that's given. Now you're going to say, why am I doing that? Isn't it obvious? Well, you'll be surprised on a test how they trick people. So I always look at this and I match it up with the number of H's. If it's less, then there's something wrong. You see that? Because if this was, let's say, added up to 5, then I know it's doubling because there's 2 H's here, 10 H's here. So it must be 2 times whatever this is. Anyway, that's just something to keep in mind. Okay, so I think we have everything we have from this, and I see some splitting. We'll deal with that in a moment. This is actually, well, let me be sensitive. All right, now another thing that I notice is that benzene has 2 signatures to it. The first one, actually, let me see if I should, well, I'll tell you now since I'm thinking about it, but I have a feeling I should come back to this one. But this right here tells me that the oxygen is touching the benzene. Do you remember why? Because when you have a separation and you could see the signals, then that's a good indication that there's an electron withdrawing group touching benzene. I went over that in the theory segment in our video, right? So I think that oxygen is touching this benzene. So and my guess is that we have an O. Now we have a carbonyl, so it's probably a good shot to just go ahead and put the carbonyl in, because whenever I see two O's, if it's not carboxylic acid, it's probably an ester. At least that's, just, it doesn't always have to be. This isn't like a golden rule, but for our course, it probably is. They're not going to separate the two. So it's either a carboxylic acid or an ester. So I'm guessing this is it right here. And it makes sense because, look, we have a CH3 and a CH2. And right now we have 6, 7. These are my other two carbons right here, 8, 9. So they're splitting each other. Notice how this is a quartet? This is a triplet. So these two are splitting each other. And so that makes sense that they are next to each other. They're not separated by oxygen. Now, the only thing that I could think of, this is the answer, but there's one other possible answer, and it would look like this, where we would have a double bond O, an O, a CH2, and a CH3. These two both would give the exact same reading in terms of positioning. But I want to show you that we can figure out, number one, based on this signature, and number two, who's furthest downfield. See, look. Well, actually, no. That wouldn't help us. So it really is coming down to the signature, because this one here, if it was touching that carbon, the benzene, and this, there would be no H's next to it. So these two would still come up the same way. So after benzene, you're going to have a CH2, CH3, and that's true for both of these, right? I guess the only thing I could think of is perhaps we can look at the allyl versus the carbon next to oxygen position. Let's go ahead and look at the numbers. Now, allyl is 2.1 if it's next to an oxygen, whereas next to a carbonyl. And then if it's next to an oxygen, actually we don't have that number. So we're going to have to use our other intuitions. So we're going to have to use another piece of logic. Okay, so in our case, they're both kind of unclear as to where they're going to fall. That's not going to be helpful. And so it really does come down to this right here. When oxygen is touching benzene, this is going to be separated. But if oxygen was not touching the benzene and a carbon was, then it would be clumped together. So this chart over here would be like that. At the whatever number this is, 7, let's say like 6 to 8.5 range. So that is when a carbon touches benzene. That is what happens when oxygen touches benzene. It gets separated out, and you could see it nice and clean. So that's it. So the answer is, in fact, this one here. But I have to be honest with you, in this type of a question, I can guarantee you that both of these would give you full credit. Okay? So don't get discouraged if you pick the bottom one, because I can guarantee you that they would both give you full credit. Okay? Because that's a very subtle detail for this semester. Anyway, there you have it. So now you get the general trend. If there's an atom that's more electronegative than carbon touching benzene, then it separates, but otherwise it's clumped together. Okay, so that covers this one here. So here we have some information, right? We have a 28 to 3150. So this is close to an alcohol. And well, actually there is no alcohol, so it's not an alcohol. So then now I'm thinking alkyne. I'll show you why. So from 28, from this number range here, from actually 25 on. Oh, okay. So this one, triple bond. So it's going to be hard to tell. This is not clear yet what this is. So we're not going to be able to get that from this chart. I was thinking that it might be a triple bond because you're upfield, but they're giving you a number that's really high up there, right? So this number here is even beyond the obvious for alkyne. So I'm not going to guess what that is. See what I did? So I thought maybe it was an alkyne. I did a quick lookup and I realized, it's a little bit beyond that, so maybe not. All right. But what I do see is 9 carbons, and I see this right here. And I hope that's clear to you, right? Here's our signature for benzene. So this is telling me I have a benzene, and it's got 5 H's, so it's got one branch. And now I have 6 of my 9, so I probably don't even need this, and I can figure out what this is. Now, let's do some integration. So I see a carbon with 1 H. Now you say, how do I know it's carbon? Because that's all they're giving us, C9H12. So I know it's got to be a carbon, and this is 6 H's. What does that mean? Remember, 2 CH3s. And so if we add everything up, we have 6, 7, 8, 9. So that's it. These are my pieces right here. And so I think it's very clear what this actually is. So this was given, but it's throwing you off. Well, at least, it kind of was extra information that you really didn't need, right? So I now know what I'm dealing with. I'm dealing with a benzene that's got 1 carbon touching it. Notice how I know this is the one next to benzene? Why? Because it's the next signal up. Whoever's here next to benzene is going to be right there. As you go further away from benzene, you're going to be further to the right. So benzene is our group that we're avoiding. Anyway, but I think it's kind of clear how this works out. We can read it almost like a recipe. This is a C with 1 H. Why? Because it's got next door 2 methyls, right? Methyl, methyl, and H. And that must be the answer. Okay? So I thought this was information that we could use, and it turns out it's not. All this was simply a carbon with an H. That's it. Or one of these H's. Actually, could be any of them, to be quite honest. This reading is going to be for all these different H types. All right, so this didn't give us anything useful. Now, the one thing I would suggest, well, actually, no, you know what? This is pretty straightforward. You don't even need to do IHD for this one because it's going to be IHD of 4, right? We know that we have a benzene that's always IHD of 4. I'll prove it to you. So C9H12 should be C9H20. We have C9H12. Right? So we're missing 8 divided by 2 equals 4. So we didn't really have to do that because we knew it was benzene, and that covers, everything here. So IHD was not needed. All right, that's it. So sometimes you'll see something interesting like this where they give you information and it really is leading you nowhere in this case, right? Nothing that we really cared to know about. All right. Number 25. So it says here that when we treat this molecule with acid, it gives us 2 products, Y and Z. So let's draw out what we have so far. So 1, 2. So I'm going to draw right now this stuff in the middle because that seems to be and this right here. Everything out of parentheses. If you recall back in the very beginning of the semester, I taught you how to break that out. I said always draw stuff that's not in parentheses first and then attach the parentheses to it. So this carbon has 2 methyls, right? So I'm going to draw that out. Methyl and a methyl. Okay, and then we have a carbon that has an H and an OH. H and OH. And then that carbon has an ethyl, so ethyl and methyl. And here's my structure. I might convert this to line formula, I'll see in a moment, with H+. Gives a molecule C6H12, so we have C6H12. The HNMR spectra of Y and Z are given below. Propose. Okay, so here's Y, and I guess the next page is Z. All right, so yeah, I don't think we really, well, okay, so I'm going to draw it out as a line formula. 1, 2, 3, 4, 5. Okay, so like that, and there's an OH. I think it's a lot easier to see it this way, right? So 1, 2, 3, 4, 5, 6 carbons, just the same as here, and it becomes that, which we know with H+. What is this? E1, right? Alcohol with acid goes through E1. So we're making an alkene. But the thing is, where's the alkene going? Well, number one, if you know the mechanism, and you kind of have to know the mechanism. I think without knowing the mechanism, it would make this problem a bit longer. But I see where they're going with this. And it's ideal if you know the mechanism. So I'm going to go over the mechanism with you right now. Now, what's going to happen here is when you have acid and alcohol, this was based on the exam 3. We said in chapter 7 that alcohols become alkenes through an E1 reaction, right? Only E1. Which in turn means what? Remember what I taught you? A number 1 is you can make into a plus symbol. So E1 means plus, carbocation. You have to remember that, especially for the next semester as well. So E1 means carbocation, just like SM1 means carbocation, because you can make a plus out of the number 1. So let's do that. We protonate this oxygen, make it leave, right? Protonates and leaves. we make a carbocation. And now what? Well, if you know the mechanism, then you'll get this answer. Because what happens is this right here is a secondary carbocation. And right next door is tertiary. Remember what we do? We always, when you make a carbocation, you stop and look for a shift. If you can shift to a neighbor right next door, then you do it. So this is going to go through a hydride shift. The rule is, if you're a lower degree and the next door is higher degree, then you try to shift an H. If there is no H, then you shift a methyl. And there is an H right here, right? So we're going to shift an H, and that gives us a carbocation like that. And now we could do our E1, because this is tertiary and everybody's lower degree, right? So no more shifting. We're going to go ahead and make the alkene. So think about it. This is alpha, this is beta, beta, and beta. Now, if you really think about it, what's the difference between this beta methyl and that? Nothing. If you put a double bond here, it's the same as putting it there, because they're both methyls touching the same carbon. It's symmetrical, right? Now you should know that very well after NMR. So we know that these two methyls are the same, which means if I put a double bond here, it's the same as putting it up there. But if we put it here, that's different, right? Over here is different. Now, this is actually the major product, right? If you put the double bond here, then you're doing Zaitsev, right? So this would be the Zaitsev product. Remember the rule for Zaitsev. Zaitsev says when you have a choice, you always pull the beta H from the beta carbon with less H's, right? This has 2 H's on it, and these have 3 H's on it. So that's going to give us the Zaitsev. If we pull the H from this yellow carbon, you get that double bond right there. And that's more stable than this one up here. This up here is the Hoffman, or the anti-Zaitsev, right? So this would be the anti-Zaitsev. And I'm confident that this right here represents one of those two down here. We don't know yet which one. We'll figure that out right now. But do you see that? So if you didn't realize, and this is a very popular type problem for a final, okay, where they give you a mechanism that you should know, and you follow through the mechanism, and then you have answers that you can match up with the chart. If you did it from here, and you tried to make an alkene this way or that way, well, if you do this way, you'll get this one right. But if you tried this one, you'd be driving yourself crazy, because you'll never get that right there if you didn't know the mechanism. Alright, so now let's figure out which one we're dealing with. Now, I can see already, I'm looking at the alkene range. Now, if you recall, this is a point where I'm just going to reference it. From 4 to 6 is an alkene. Okay? It's actually, I went a little bit broader. It's like 4.5. Well, actually, no, it's fine. 4 to 6 is an alkene. And we have an alkene right there. That's a blow up, right? This is a blow up box. So this is the alkene, and it's right there. This one is a triplet. You could see its blow up right there. And this is a doublet, and this is a multiplet. You see that? Okay. Now, what am I going to do with this information? Well, the first thing I'm going to do is realize that this alkene has only one H. So which one of these has only one H? And that's it. That was as easy as that, actually. So this one has one H on it. So my bet is that this right here is the answer for above, because that has only one H on the alkene. And that's what the integration told me up here. Now, if you want, you could add up. Total number of H's should be 12. And we have 3, 6, 9, and then 12. So we knew this was the right number, and only one H on the alkene. All right, so let's go ahead and figure out what this looks like. So let's draw this up here, and let's label out where things are. So make sure I'm not missing, right, ethyl. Okay, good. All right, so I think it's clear that this H right here belongs to the one that's furthest downfield, right? Because think about it, this is on a double bond carbon, and these are all single bond carbons, so definitely going to be to the right, to the right. Sorry. When I teach in front of the camera, my right and left are switched, and then when I teach like this, my right and left is your right and left, so it gets a little confusing. Anyway, so this right here, so let's go. So let's label this one as A, this is B, this is C, this is D. All right, so this right here must be D, right? Now, think about which one's A. is it the methyls touching the alkene, or is it the methyl furthest away? And I hope you said the furthest away, right? That's A for sure. And it becomes a triplet. See that? Because there's only two neighbor H's plus 2 plus 1 is 3, right? So that's that. And now let's think about these right here. Okay, now clearly between this one and that one, these are methyls, and this is a methylene. Remember the rule? Methylene is further downfield than methyls. So this one must be the one that's right next to the alkene H. And sure enough, it says CH2, and that is a CH2. So this must be C, because that's a methylene, 2 H's, versus a methyl, and when they're touching the same electron withdrawing group, the methylene loses. And that's how I got to that. All right. Now, what about these two methyls? Well, that's a little bit tricky, actually. And, you know, let's see if there's any hint from this pattern. It doesn't. They're both singlets, it's saying, the two methyls. Let's see. Oh, actually, it makes sense. Okay, so if there's an H here, it's 1, 2, 3 away. There's no, so 1, 2, 3, or 3. There's no H coupling it, so they are singlets for sure. But now we have to guess, is it better to be across from an H, or is it better to be across from a carbon? And, you know, to be quite honest with you, they're very close together. They almost have the same signal at the base. And the reason why is because they're very close. But if I had to guess, I would say, I guess a methyl is better to be next to a methyl than a methyl would be next to a carbon, because, a methyl next to an H rather than a carbon, because we know that methyl is better than methylene, methine, so being next to an H is probably not as bad as being next to a carbon. So I would say that, and again, this is pulling hairs, but I'd say this is B, and this is, they're just, yeah, okay. So that would be B. I see, so this is D and this is E. So let me just fix that. All right, so we have A, B, C, D, and then E, right? So A, B, I'm going to say C, and then this is D, and then, of course, the H here is E. Like that. Okay? So, again, this was splitting hairs. These two are very, very close together. And the reason being is because there's not much of a difference between them. Okay? All right, but that's it. So now, clearly, this is the answer. We've matched up our patterns to see that everything works, right? These are singlets, as expected. This is a triplet, A. And D is going to be a multiplet because it's got A as a neighbor and then it's got E. It's definitely n plus 1 times n plus 1. And that's what we see here, a whole bunch of lines. This is a multiplet, right? So everything matches exactly as expected. Now, why is this a triplet? Why is this 1H a triplet? Because it's coupled with D, right? This is 2H plus 1 is 3, and that's how we get a triplet. All right, so hopefully this is clear, and I like this problem as well. I thought this was a really good problem. Now let's figure out Z. Well, I think we know what Z is now, right? So let's go ahead and take our other answer and see if that works out to be Z. So let's do that right here. All right, so this is what I'm guessing is Z. And really it comes down to just doing our analysis, right? So this is the range right here for alkene from 4 to 6. And so we have a 2H, and that makes sense. There's 2 H's. They're coupling them. Now, are these 2 H's really different? Probably, are these 2 H's really the same? And the answer is no, they're different. But because one's across from a methyl and the other's across from a propyl, they're both across from carbon. So in this analysis, this is a real chart, by the way. These aren't imaginary. These are actual charts that have been printed out. So this right here is coupled together. It really is two separate readings, but you won't see it because of how close to in electron environments that they are. So they are different, but you wouldn't see it on a chart like this. This is probably a weaker magnetic field. If you had a stronger magnetic field, you would see a clear separation between these two. But that is, in fact, 2 H's, right? Okay. Why is it a doublet? it should be 2 doublets. And the reason why is because this one is split by that, and that's split by that. They're splitting each other, but they're too far from the other H's. So this is, for this one, it's this plus 1 is 2, and for that one, it would be that plus 1 is 2. So they are doublets, but again, if this was a strong enough magnet and a higher radio frequency, you would see 2 doublets here, right? Okay. Now, what about this guy here? Well, we know it's one of these two, and what's worse off, methyl or methylene? And I hope you're saying methylene. So I'm guessing that this right here is the methylene, because methyl's better than methylene. So this is probably, let's just label this out. So if this is A, B, C, D, and then E, these are E, both labeled together as E, although we know they're really different. If they asked us on a test, we would have to say these are different. But in this chart, they looked like they're the same. All right, now this is definitely D, right? Right there's D. 2 H's, and it's further downfield than a methyl. But the next one up should be methyl, right? And it is. See how that methyl's here? See, that methyl is still touching an alkene, so it's worse than this one or that one. So it's not that methyl always wins to methylene. Notice how this is a methylene, but it's only when they're the same distance to some electron group. So this is definitely going to be C right here, and then this one's going to be B, and this one's going to be A, right? So let's double check. A should be a triplet, and it is. Right, so A is a triplet. B should be a multiplet, and right here's a multiplet. You can see that, 2H multiplet. And then C is a singlet because there's no H3 bonds away from this H up here. So yep, that's good. And then the rest we already proved. That's it. So there you have it. And by the way, this is a triplet because it's split by B, but it's not split by C, right? C is too far away from this H group down here, and these are too far away, right? It's 1, 2, 3. So you're never going to get from this H to that H 3 bonds away. So that's why it's only split by B. All right, guys. So I know I'm doing a very thorough job, and I really want to. In case if it's confusing, I hope this is making things easier for you. So remember, we did A, B, and C together, right, as the part of our theory practice, and so now we're just going to go ahead and solve the rest. Now, I'm looking at this here. Now, let me just remind you a few things. The first thing is you have a formula, you have your locations, you have a split pattern. Singlet is S, multiplet M, Q for quartet, T for triplet, right? So that's that. Integration is the number of H's that represent each signal, whereas this represents the neighbor splitting pattern because of a neighbor. And then if you have IR, it's provided over here. What's the first thing I told you guys to do? When you see a problem like this, where it's written out instead of a chart, you make a chart for yourself. Always start that way. It doesn't matter if you have the exact numbers, although you should look for signature numbers, which I will remind you about in a moment, but just put the relative locations on this diagram for yourself. So singlet, singlet, multiplet. So singlet, singlet, and multiplet. Now, I automatically see my eye running to this number because when I have a big amount of carbons, I automatically look for this signature here. Remember, 6 to 8.5 is a benzene, right? And you should always look out for that, anything in that range for benzene. So this is definitely a benzene, right? So I'm going to write that down, 7.28, because that's going to be important for me. 5 H's, that's the integration. So this is 5H, this is 2H, this is 1H. Now, this tells me, remember, benzene has 6 H's around it, but every time it has a branch, it loses 1 H. So if this had 4 H's, it would have 2 branches, but it has 5 H's, so that means it has 1 branch. So now I know that this is a benzene that has 1 branch, Z. Okay, this right here, might as well finish up with this part. This right here is a CH2. And this right here is a CH, but keep an eye out. Look right here. What's that number? This is broad 3000 plus. This is an OH. Now, what do we know about OHs, by the way? We know that alcohols don't split or get split, right? So they don't split neighbors, and neighbors don't split it, right? So that's the rule with alcohol. And the reason why, remember, is because of proton exchange. This is constantly losing its H and gaining an H and losing an H. So the chances of it being present during a chemical shift interference is unlikely in either direction. So, okay, so that's that right here, right? This is our signature. So now I know that this is not a CH, this is actually an OH. Why? Because it's a singlet and it's 1H, alcohol. This is a singlet, but it's not 1H, it's 2 H's, so it must not be the alcohol. All right, so now this is everything I need to know. And actually, I could piece this together analyzing what I just did. So here's what I'm looking at. We've got 7 carbons, 1 oxygen. I mean, you could add this up right here, and you'll get to 8, right? Same number of H's. Okay, so we don't have to worry about extra H's missing somewhere, or multiplying this by 2, or dividing it by 10, or something like that. So we're good as is. But this is a very easy chart to read. I know this is benzene, and that's the one that we're avoiding. So remember, alcohol is not predictable. It can be anywhere in this chart, alcohol. So the alcohol range is too wide to actually write it down as a certain number. That's why in my card, I don't show you the alcohol reading. I tell you just to keep an eye out for a singlet that has 1H on it. That's it. So this is the alcohol, happens to be furthest upfield because the benzene seems to be doing more damage to the neighbor than the oxygen does. Anyway, let's take a look and see what's going on here. So I've got 6 carbons, and really there's only 7, so it must be a benzene that has a CH2 and then an OH. That's it. That has to be it. This is the only possible scenario. The O couldn't be on benzene because then this would be 4 H's, not 5 H's, right? So it had to look like this, and it makes sense. So this is a CH2 singlet. Why? Because there's no neighbor H here. Remember, it's 3 bonds or less away. And this one, if you count this out, let me just review that since we're doing. So if you count this out, it's 1 bond, 2 bond, 3 bond. And remember, benzene has only 1 bond per carbon, so there's no H here, right? If you look at the actual structure of benzene with the double bonds, this has 4 bonds. It doesn't have an H. Every benzene carbon has only 1 bond sticking out. And so that's why this is not going to do any coupling. These H's are too far away. They're 4 bonds away. And this is not going to couple because even though it is the correct number of bonds away, it's 3 bonds away to this H. The problem is that they don't split each other. Alcohol doesn't split or get split. And these two are the same, right? We already know that from our basic, theory review stuff that we did, so I'm not going to bother. But these two on the same carbon are the same. So this is in fact the right answer, and everything matches the pattern up here as we see it. Okay, so there you have it. Don't worry about this alcohol. Sometimes it's here, sometimes it's there. I mean, well, it probably won't be past this one, but it would be here or it could be here. So don't worry too much about where that falls. All right. So here we have C4H9Cl. We have some chart, and so let's go ahead and start that way. Let's put this into a nice diagram that we can visualize. So this is a doublet, and this is a multiplet, and then a doublet. Okay, now clearly I don't care about benzene because that's not even 6 carbons, so I'm not going to look for that number. And there's no oxygen, so I'm not going to look for carbonyl or an aldehyde or carboxylic acid number. So really I'm just going to work this as is. Integration is the key here. I could see it already. So this is 6 H's, 1 H, and 2 H. Well, what do I know about 6H? It's either going to be one of 2 things. Either it's 2 methyls or it's 3 CH2s. With this formula, it's probably not possible to have 3 exact CH2s. It's too small of a formula, right? So this is probably, and I'm pretty sure it is, 2 CH3s. That makes sense. You could have 2 methyls touching the same carbon, or maybe symmetrical across a line, a straight chain. But I'm guessing it's on the same carbon because this is a very small chain. There's only 4 carbons. We already know what 2 of them are. Now this is a CH2 and this is a CH, right? The Cl can't have an H because it only makes 1 bond. So this is definitely a CH2 and this is definitely a C with 1 H, 3 bonds. Okay, so here's what we have so far. And I think we're pretty much ready to go. And by the way, if you look at integration 6, 7, 8, 9, and that's 9. So we know that we're right. We don't have to multiply this or divide this. It's perfect as is. Okay, so now let's go ahead and solve this problem. I'm pretty sure I know where to begin, and I think you do too. It's by the methyls. I'm guessing, and if this wasn't right, we could always try another way, but it's either going to be where you have a straight line and there's a methyl here and a methyl there, and there's a plane of symmetry that way, or the way I'm guessing is that there's two methyls on the same carbon. That makes sense to me because it's such a small number of carbons that this is already 3 of our 4, right? So this is probably what it is. So that's 2 methyls touching 1 carbon. Now, does that carbon have, well, this carbon has to have another carbon, right? That's the only possible thing. There's nowhere else to put the carbon. It's 4 carbons, so let's put it here. And now the question is, does this carbon have the Cl or that one? Well, think about it. There's a carbon with 1 H. And if we put a Cl here, then we're going to have 3 methyls. So that can't be the place for the Cl. The Cl must be here. So this must have an H, and this must have the Cl, because now we have a CH2, we have a C with 1 H, and we have 2 methyls. So this is definitely the right answer. And now let's do, as always, let's label this out. So if this is A, B, and C, well, we know this is C. Closest to the electron withdrawing group, this is what I'm worried about right here. Whoever's closest to that is losing its electrons more. So this is C, this is B, and this is A, right? They're both methyls on the same carbon. So that's our guess, A, B, and C. Okay, remember I label the carbon, but what I really mean is the H is on the carbon, right? Okay, you'll see that actually this is useful because CNMR, it's the same way to label it because of the way I do it. CNMR, HNMR, they label the same way. Okay, anyway, so these 2 methyls are going to give 1 reading because they're touching the same carbon and they're identical. And that's 6 H's. And since there's 1 H neighbor, that means that these 2 are split by B, and it's going to be a doublet like that. 1 plus 1 is 2. This B is going to be split by everybody around it. And now, is the C side different than the A side? Well, slightly. I'm not sure if this is enough to do n plus 1 times n plus 1, but for sure, even if you don't have to figure that out, this is a multiplet. And so whether it's 3 and 3 for 6 plus 1 is 7 times 2 plus 1 is 3 times 3, that's possible. Or if it's 6, 7, 8 plus 1 is 9, either way, it's a very messed up reading, right? You're not going to see that many lines. So we don't care. If I had to guess, I would say it's just n plus 1. I don't think 1 Cl is going to make it such a big difference between this side and that side. But the truth is we don't know. Remember, this is all about the J that I talked about, right? The J. And so we don't know if this is actually enough to actually make a difference. But it doesn't really matter. So this 2 here, the C, they're going to be split by B only because that's the 3 away. 1 bond, 2 bond, 3 bonds, they're coupled. And so these 2 are split by B into a doublet. And that's it. So we've proved it, we've checked it, and we know we can move on. All right. If anything doesn't make sense, make sure you go back to the theory videos, right? Because this is at the end, after 8 hours of a lot of theory that we went over. This is the wrap-up final video. Okay, so here's a huge formula, and I'm praying that there's something in the 6 to 8 range, right? 6 to 8.5, and sure enough there is, and I'm very happy to see that. Okay, that was the first thing I saw. I was intimidated by that 15, and boom. And actually, this is special right here, right? We'll look at that in a moment. So let's go ahead and just put this out into a chart. And we have definitely have a multiplet, M, and that's 7.25. That's our benzene. I always write it out so I don't forget if I happen to go talking or, thinking about other things. So that's definitely an important signature. And it's got 10 H's. I hope you're thinking about what I'm thinking, right? Which is benzene should have 5 or 6 H's, 1 branch, 5 H's. Well, that's exactly, that's double that, right? 10 divided by 2 is 5. So I'm guessing it's 2 benzenes, which is fantastic, right? That's 12 of our 15 carbons already done. All right, anyway, let's keep going. So we have a singlet and we have a singlet. The singlet over here has 1 H and this has 3 H. All right, 1700, I'm thinking C double bond O. When I see an oxygen and I see 16 to 1800, I just think double bond O to begin. If I'm wrong, then maybe it's double bond C or something else. But this is probably right, especially with the O. There's nothing at 9 to 10, so I know it's not an aldehyde, not aldehyde, right? There's no 9 to 10. All right. Now, is there anything else that we can do? Well, I think I'm kind of excited to get started here, right? Because we got this 2 benzenes that I know about. But let's just think about the relationship over here. Well, we have an alcohol. The benzenes have one branch each, right? Because it. Let me think if there's a way for it to be like. No, it couldn't be. So the fact that it has to be like benzenes with one branch each, like that, 2 times. The question is, are they? Well, they're not connected directly to each other, because if they were, there would be no room for anybody else. So it must be a symmetrical thing. Now, I'll tell you why. Let's say that this didn't, like, how do I know that this is symmetrical with the next benzene? So in other words, how do I know that somehow it's going to look like this? And then there'll be a plane of symmetry. Because the fact that all 10 H's are giving one reading means that it's identical. If it wasn't symmetrical, then you'd have 2 readings at 5 H's each. You see that? So that's why I know, and it would still be within the range of 6 to 8.5. So the fact that it's one reading for 10 H's means that there's symmetry here. All right, so let's keep that in mind. Now, we still have to deal with an alcohol, and I'm sorry, no alcohol, a carbonyl. And then there's singlets. So what are we thinking? Well, what I'm thinking is that this carbonyl is going to somehow be in the middle so that these guys are not next to each other. Remember, this is a 3H, so that must be a methyl. And this is a 1H, so it must be a carbon with 1H. Now, if they were next door neighbors, they would split into a doublet and a quartet, right? If they were neighbors. So I'm thinking we're going to use this to separate these two from each other. Okay? Let's see how we can do that. So we have a benzene, and then we could try the carbonyl here. Oh, actually, if we did that, now we'd have to go carbon-carbon. So that doesn't make sense, right? We shouldn't do that. What if we have a carbon? Now we have a 1H carbon, so, and then we have a methyl. So, so what we could do, let's think, is put a carbonyl here. And now what I'm doing is I'm separating this carbon from anybody else. However, I've got 1H and a 3H, so if I did this, I would be good for this methyl. This methyl would be separated from this one. The problem is this says 1H, and this has 2 H's, so I must be missing something. Let's see. C15. Oh, sorry. I see what I'm missing. Basically, the problem is that there's a second benzene, right? So I'm guessing that it's not like this, the benzene, because if it was like that, then this would be a CH2, not a CH3. We know there's a methyl, so we could put the second benzene here, right? And that would make them identical because they're on the same carbon. So if we have a second benzene right there, now we've got ourselves the answer. So all I knew was that we had a carbonyl, and we knew it wasn't on the end because there's no 9 to 10. And I also knew that these two groups aren't splitting each other, so this is used as a wedge in between them to make sure they don't split. So I knew that was happening, and I also knew I had 2 benzenes. So at first I thought it was benzenes across, but it turns out they're on the same carbon. And this is perfect. This gives me 1H, this gives me methyl, and now let's analyze our pieces. This should be furthest downfield next to the benzene, right? Furthest is benzene, and then the 1H right next to it. Why? Because it's got 2 benzenes pulling the electrons away from it, making this the most de-shielded besides the H's on benzene. And that's it. So this is actually worse than having it next to a carbonyl. Now, I think that makes sense because benzene is further down than carbonyl. So allylic, well actually, no, let me show you something. Let's go back to, this is an important part. When you have a allylic, there's allylic in 3 different ways that I showed you guys. One way is allylic next to carbonyl. Another is allylic next to benzene, which is called benzyl. And if you have 2 benzenes, it would be even worse. It would be shifting even further down, right? So that makes sense. The carbonyl H next to carbonyl is not as bad. Allyl of a carbonyl is not as bad as next to benzene. And so everything supports our answer. We're good to go. So you see how logical it is, and everything supports. I strongly encourage you, this is the answer, I strongly encourage you to always check your work, because they could do a subtle change that maybe there's more than one answer and only one would be right. So you got to keep an eye out for that, okay? All right, let's do G. So here we have a lot of information. We have IR, I see a whole bunch of IR. So let's just do out our chart. right? So we have a triplet, and then we have a multiplet, and then we have a triplet, and then we have a singlet. Now, I see a number that I want to keep in mind right there. That's a big number. And anything that's greater than 10 is probably carboxylic acid. And there's two O's here. See that? So I'm guessing, since this is 10.97, it's a carboxylic acid. That's my guess. Cool. So that right there, that's 1H, 1H, 2H, and 3H. Okay, so let's actually finish up with this idea here. So this must be a methyl, a methylene, methylene, a carbon with 1H, methine, and then this, of course, is our OH from carboxylic acid, right? So that's the OH of a carboxylic acid. We might as well draw that whole thing in. So there it is. These are my pieces right here. And notice it's 1, 2, 3, 4 carbons, and that's 4 carbons. So we know we're right. If we count up the H's, it should be 7. 3, 5, 6, 7. We're good. So this is it. We have a lot of information. I'm anxious to get started, but the last thing I'm going to do is this is verifying that we have our 2 pieces for a carboxylic acid. All right. So now let's keep in mind we have a Br here, right? Because I'm going to use that somehow. And if I don't say that to you and to myself, I might leave it out and say, hey, why am I not getting it right? So this is important for me to do and for you to do on your test. Always keep an eye on something that, because otherwise I've done it before plenty of times where I'm drawing it out and I forget that there's a halogen because I go down the page like that and I don't see the formula. Okay? So keep in mind there's a Br there. So where do we begin? I think it's actually, this is easy. This is read like a recipe. I'll tell you what I'm looking at. I have a carboxylic acid, and this is the carbon that's right next to it, and this is the one further away, and this is the one further away. See how it reads? This is the most de-shielded, and whoever's next to it's closest to it. So let's do that. We have a carboxylic acid, and then the carbon right next to it has how many H's? 1H. So let's do that, 1H. And then it's next to a carbon that has how many H's? 2 H's, right? So CH2. And then that's next to a carbon that has 3 H's. See how I did that? Very simple. I like these type of readings are great because it reads very simple. And they're not always that easy, but this one is. And look at that. We have CH. Why is that 1H? Because there's a Br and it must be right here. That's it. This is the only one that has an H missing. This is a CH2, which is supported right there. This is a CH3, which is supported right there. So this must be where the Br is. This is definitely the answer, right? Makes sense. Carboxylic acid H is right there, right? So if this is A, B, C, and D, this is D, this is C, this is B, B, A, and A, right? Methyl split into a triplet. B is split by A and C, and it's either going to be 3 plus 1 times 1 plus 1, right? So 4 times 2 is 8. You're not going to see 8 over here. So we're not sure, but I'm guessing it definitely is because this side here is very different. It's got a lot of electron withdrawing groups on it. So I'm guessing the JBC is definitely different than JBA, right? So JBC, I'm guessing, is not equal to JBA. Remember what I said to you guys in the theory? I said whenever you're looking at the H's, if the neighbors are very different, like if there's a lot of electron withdrawing group on one side over the other, then you know this is true. All right, so I'm guessing this was actually 3 plus 1 times 1 plus 1. That's my guess. Anyway, we didn't have to worry about that for this. And then finally, 1H right here is a triplet because C has only B as a neighbor. 2 plus 1 equals 3. Okay, there you go. Okay, for H, well, my eyes automatically jump right to that. I hope you're starting to do that too after all the work that we're doing together. 7.23, it's a multiplet, and then we have a quartet, and then we have a triplet. Okay, so there you have it. So there's my pieces. 5 H's, so I know benzene has 1 branch, right? 1 branch. 2 H's, so I know that's a CH2. And 3 H's, so that's a CH3. All right. Now we have a benzene that's 6 carbons, and then 2 carbons makes 8, and that's exactly what we have. So we're good. This is perfect. 5 and this right here makes 10, right? So 10 H's, 5, 2, and 3. So we're perfect as is, and we're ready to solve this problem. Not much to it. This also reads very easily. You read from the benzene and you work your way out. So this is closest to benzene, this is furthest away, and it's really simple. It's just benzene, CH2, CH3. So benzene, CH2, CH3. That's it. That must be the answer. And this has 5 H's because it's got one branch, and everything else is clear. I think this is pretty straightforward. All right, so let's go ahead and look at this one right away. My eyes call to that right there. I always, always look for those big numbers, right? 9 to 10, aldehyde. 10 to 12, carboxylic acid. Okay, so we have a carboxylic acid, right? That's what that tells me. So 10.95, we have a singlet, and it's 1 H, of course. That's the carboxylic acid H. Then we have over here a singlet, which is 2 H's. We have a quartet, which is 2 H's. And we have a triplet, which is 3 H's. So I think this is all clear, right? We know what this is. This is a CH2. This is a CH2. This is a CH3. So let's write that in. CH2, CH2, CH3. All right, and this is a carboxylic acid. Now, we already got our 4 carbons, and that's what we're dealing with, 4. But we still have an extra O. So in this case, we have an extra O that we have to deal with. This right here tells me alcohol. That tells me carbonyl. So that's further supporting that this right here is correct, that this is a carboxylic acid, right? Because remember, carboxylic acid, or I should say aldehyde, can go to this level. So remember, these are general ranges, so it's nice to have reinforcement here to confirm. But that's all it did. All right, I'm ready to build this. It's pretty easy because we're going to do the same thing. Now, here's the thing actually I want to make clear. This third O is not an alcohol because well, actually, the truth is you don't know from this if it was an alcohol. Maybe there's 2 alcohols, right? Well, how do I know it's not an alcohol? As I was saying it and I was correcting myself, my eyes dropped down. And what was I looking for in here? What do you look for if it's an alcohol? Think about it. A singlet. This is a singlet, but it doesn't have 1 H. This singlet, we know what it is. It's a carboxylic acid. So if this said 1 H, then it's possible that there were 2 alcohols. One for the carboxylic acid, OH, and the other for an alcohol. But in this case, there's no alcohol, right? So that means that this third oxygen is really going to be used as an ether. It's going to be somewhere in the middle. And now let's figure out how we can work that out. All right. So here's what I'm going to do. Very simple. I'm going to read left to right. Remember I taught that to you in the theory? I said I always start either in the extreme, left or right side of the chart. I'm going to read from the left. So carboxylic acid, for sure. And now it's next to a carbon that has 2 H's. And then it's next to a carbon that has 2 H's. And you say, well, if this was the case, if this CH2, which I know for a fact is next to carboxylic acid, so that's right there, right? So if this is A, B, C, and D, I know this is D, right? And I know that this is C. What's the problem with C? C right now, if it has a CH2 next to it, is going to be split into a triplet. But it's singlet. So now I know where that extra oxygen goes, right? The oxygen is wedged in between in order to prevent this from splitting. So actually, I now figured out that there's an O right there in the middle, and now this is going to be a singlet because there's no neighbor 3 bonds away to an H. 1, 2, 3, and so this is it. And now I can continue with what I was doing. So this is a CH2 right there, this is a CH2 right there, and then finally connection to the methyl. Pretty easy, right? Now you should prove to yourself that this works, but I know it does just looking at it, so I'm not going to bother because I know this video is going to take longer than expected. So this is, I'll say it real quick, this is a triplet, triplet, this is going to be a quartet, quartet, this is going to be a singlet, singlet, and this is a singlet, singlet. Okay. Okay, let's do J. So for J, let's go ahead and read out this chart. We have a septet. I'll just make it a multiplet, 1H, and then we have a doublet, which is 6H. Okay, so that's all we have, and we have a form C3H7NO2. Oh, okay, NO2. This is interesting because I'm pretty sure that this right here is an NO2, literally, as written out. I don't think you're going to break it up into yeah, this is a confusing problem because this right here, you might have tried on your own to put the N and the O on the carbon and play around with it, but really that nitro is actually as is. NO2 is an N double bond O, single bond O minus, and then this is connected to R. This is positive. That's an NO2. But I don't think that you would really know to do that. So this is a bit hard for that reason. I could see this problem driving you crazy if you try to put the N and the O. All right, well, let's see. I mean, yeah, this is just, I don't like this problem because I don't think you're familiar enough yet with nitro, the NO2 group. Anyway, but that's my guess, and let's see if there's other information to help us out. Well, 6 H's, that's 2 methyls, right? And this is 1 H, so it must be a carbon with 1 H. Now, you might have thought it was an oxygen with 1 H or something else like that, but if it was an oxygen or a nitrogen with an H, then it would be a singlet, not a multiplet, right? Remember how OH and NH don't split or get split, so I know this is a C with the H. So I guess this is enough, maybe, but I still think this is a hard problem. Well, there's only 3 carbons, and I have 2 methyls. It must be on the same carbon. Otherwise, it would give different readings, right? It would be 2C. It would be a H3 times only, not 6. So my guess is we have this with a methyl twice. And now I know that there's 1H carbon, so there it is. And so then it must be attached to an NO2, right? NO2. So that's actually the answer. But I have to say, I'm pretty sure this would drive someone crazy, because it would, it would take you forever to realize that nitro is a group. It's not breaking this N and O up, right? Or O2 up. Anyway, this is the answer. Let's double check. So our methyls are the same, and they're going to be split into a doublet. There's 1 H next door. And our 1 H is split by 6 plus 1 is 7, septet. And so this is definitely the answer. Again, I think this was a bad problem because the NO2 would throw people off. All right, this one I noticed that when I printed it out, it actually cut this part out. I don't know if the packet that you guys have has this in there, but I noticed that it was cut out when I took the screenshot. Okay, so let's go over this one here. We have a chart, and we've got a singlet and a singlet. We have a 6H and a 4H. Okay, so I know that this is 2 CH3s. And this is 2 CH2s, right? Remember that? I showed you guys. So if you have a 4H, it must be 2 CH2s. 6H, it's 2 CH3s. It's unlikely that it's 3 CH2s, right? Okay, so, and then notice that we have these 2 oxygens to deal with. Well, the fact that I have 4 carbons and I only have 2 readings means that it's symmetrical. Remember that? Remember that trick I showed you? And this is the only time we're actually using it, but in this case, it looks like it's warranted. Whenever you have less chemical shifts than the number of carbons, and especially if it's exactly half, then it's definitely symmetrical across a line, right? So we have a linear structure, and somewhere in the middle is a symmetry. That's how you would get only 2 chemical shifts, even though we have more, like we have 4 carbons. So it would be these 2 being the same as those 2, right? And that's how you get that. So now I know I'm dealing with a straight line with symmetry. So now why did I say that? Because if we started out, we might have put the 2 methyls on the same carbon like that. But that's actually not the way we're going with this one. And I recognize that because there's only 2 chemical shifts. If there was more chemical shifts, then yeah, sure, we can put 2 methyls on the same carbon and build from there. But in our case, we have these O's, we have symmetry, so, and everybody's singlet, so my goal is to make sure that everyone is separated by an oxygen. So here's what I'm thinking. I'm thinking CH3, separate with an oxygen. CH2, separate with an oxygen. Well, the problem is we don't have enough oxygens for that side, right? It's not symmetrical. So that's not going to work. But do you remember that when you have neighbors that are the same, they don't split each other? So what if instead we have CH3, oxygen, CH2, instead of oxygen, what if instead it was like this? CH3, oxygen, CH2, CH2, then oxygen, CH3. See that? This right here is a plane of symmetry, which means that if this is, let's say, A, this is A. And if that's B, that's B. And since B are the same, they're not going to split each other. The only time you have a chemical split or a signal split is if it's different than the one that's doing the resonance. So when neighbors are identical, they don't split because they resonate at the same time. The ones that are relaxed as neighbors are the ones that can interfere with the message when you go through the decay, right? When the beta goes back down to alpha. So this was pretty interesting. This is definitely the right answer. It's the only answer that makes sense. And again, I kind of jumped over some, but I saw it here in my mind. I know that there's 10 H's, and so this is an alkene. It's not an alkene, right? 4 times 2 plus 2 is 10, and that's what that is. So I kind of did that in my mind. But here it is. So I think this is clear. If you see a chemical shift, a chart that has half of what your formula is, there's a good chance there's a linear symmetry. Now, it's not always true. I mean, you could have symmetry like that, right? And that's actually, that would be linear as well as horizontal, but, you know, vertical and horizontal. But just keep that in mind. When you have symmetry, when you have half the chemical readings than you do number of carbons, then that's probably the case. All right, guys. So that covers the last problem, and I believe I left 2 more for you guys to do on your own, right? So you have enough. You've solved with me plenty. And that's it. I mean, I'm going to work on the workshop next, but this is enough for you guys to really have a good handle on how this works. All right, so I'll see you guys soon.